Right, this video will go through questions 25, 27, and 29 from textbook page 43. So we're going to start with 25. So let's read the problem. A car traveling at 45 kilometers per hour, that's a new unit here, slows down at a constant 0.5 meters per second squared just by letting up on the gas. Calculate A, the distance the car coasts before it stops, B, the time it takes to stop, and C, the distance it travels during the first and fifth seconds. All right. So that last one we'll talk about a little bit. But so let's first talk about what's happening here. So a car traveling at 45 kilometers an hour. So you have a car, and it's traveling at 45 kilometers per hour. It's going to slow down at a constant rate, which is A, and it's going to slow down, which means it must be negative 0.5 meters per second squared. That's the acceleration here. Okay. All right, and calculate the distance the car coasts before it stops. So we are wondering at what point it's going to have Vx being 0 kilometers per hour, or let's say meters per second, because that's what the variable, the unit we usually use. Okay, so let's just do that one first here. So we're looking for the distance. So we're going to say here, we're going to call this x0, and how far does it travel to position x before it slows down. All right, so Vx0, the initial speed is 45 kilometers per hour. Final speed, Vx, is 0 meters per second. Acceleration is negative 0.5 meters per second squared. And our initial position we'll say is 0 to simplify things, and our final position is our question mark. How far is it going to travel? So you can see here, the way I look at it, I say, oh, there's no time here, right? There's no time in our equation. That means we must use the third equation. But I also noticed that there's something weird with our units here. The initial velocity is in kilometers per hour. We don't want it in kilometers per hour, so we're going to have to do something called dimensional analysis, or sometimes it's very similar to stoichiometry from chemistry. So that'll bring back good memories, I'm sure. So let's start out by figuring out what is going to be Vx0. So we start with 45 kilometers per hour. Okay, that you can say it's per 1 hour or whatever. So we have to change it to meters per hour. So, sorry, meters per second. So first, let's get rid of the kilometers. In 1 kilometer, there are 1,000 meters. Where that way the kms will reduce. And then in 1 hour, I'm gonna run out of room here. How many seconds in an hour? There are 60 minutes times 60 seconds, so it's 3,600 seconds in 1 hour. That will allow the hours to cancel out, and what I'm left with will be meters per second. So this is just changing the units here. So 45 times 1,000 divided by 3,600, and I get 12.5 meters per second. Okay, you could have just plugged this into Google and said, what is this in meters per second? And it'll give you the answer. You won't have Google on the AP test. It's very rare, actually, that they make you do this unit changing. The book makes you do it all the time. The AP test, it's very rare. So, but it is useful to know how to do just in case it shows up on the AP test. All right. So we've successfully did our dimensional analysis here, changed our kilometers per hour to meters per second. Now I know I wanted, let me write down the equation here. We had I said we even wanted that third one. Vx squared is equal to Vx naught squared plus 2ax times x minus x naught. So we are rearranging the equation to find x again. We actually did this in a previous problem. but it is good to practice it yourself again. Again, I'm going to cross this out and say that's 0 to simplify things for me. All right. You could also do that with Vx if you want as well, but I'm just going to do it this way. So I'm going to start by subtracting Vx 0 squared from both sides, so that side reduces out. And I have Vx squared minus Vx 0 squared is equal to 2ax times x. Gonna divide both sides by 2ax, so that reduces out and leaves me with x is equal to Vx squared minus Vx 0 squared over 2ax. So you can see I just flip-flop the sides again because it doesn't matter in math whether one side is on the equals or not. But that allows me to plug in my numbers now. So Vx is 0. So that squared is just going to be 0 minus 12.5 meters per second squared divided by 2 times negative 0.5 meters per second squared. Again, that squared is just for the units. We're not actually squaring the negative 0.5. It's just telling you that that is an acceleration unit. Notice up top, the 12.5, the whole thing will be squared. Not the negative, though. What else? Oh, that 12.5 is the meters per second. If you had kilometers per hour there, the units would not match, and you couldn't do the equation correctly. So make sure you have the units correctly. So 12.5 squared is 156. We get negative 156.25 meters squared per second squared, because both units are squared, divided by 2 times negative 0.5, which is just negative 1 meters per second squared. All right, and you can see actually this second squared cancels with that second, that squared cancels with that m, and we're left with just meters, which makes sense because distance is, the negatives also cancel out here, so those cancel out to be 156, positive 156.25 meters. So that is how far the car is going to travel before it stops, just by letting up off the gas. So that would be what, like over 300 feet. So probably almost 400 feet. All right, the time it takes to stop. So how long is it going to take in terms of time? So we could either use that first equation or the second equation. If you look at the second equation there, if you use that one, that is if you look at time as like the variable, that's a what do you call it, quadratic equation. So you probably don't want to use the second one. Let's just go with the first one so we don't have to do any quadratic formula stuff. All right, so let me use a different color. So we have Vx is equal to Vx naught plus AXT. So we're going to solve for t here. So I'll first subtract Vx naught from both sides so that reduces out. And so I have Vx minus Vx0 is equal to Ax times t. I'm going to divide by Ax from both sides. That reduces out, and I'm left with t on one side by itself, which is t is equal to, again, I'm just flip-flopping the sides to make it simpler on my mind here. So we have Vx minus Vx0 over Ax. Just going to plug in my numbers. Vx was 0 meters per second minus 12.5 meters per second divided by negative 0.5 meters per second squared. Again, we're not squaring the number, just the units telling us that that's an acceleration. So all we do is negative 12.5 divided by negative 0.5, and we get a positive 25 seconds. That's how long it takes for it to slow down. Now, imagine that I got a negative number there. Could we have negative time? No. If we had a negative distance, we know it's just going to the left or backwards, right? But if we had a negative time, there'd be a problem because we can't go back in time in physics. That's impossible. So having a positive there makes it clear to me that I did it a little bit right, at least, okay? If you had gotten a negative there, you probably forgot the negative on the bottom or the negative on the top and you did something wrong. So it's good to double check that. By the way, I keep forgetting to do this, but you really should, at the beginning of these problems, label one direction as positive. So I'd say to the right is positive, up is positive. Or to the right is positive, down is positive. Or you could label the left positive. But usually I'm going to call right positive. It's called just a reference frame for us. That way everybody can see, oh, that's what is positive. So I would label that positive X and positive Y. We haven't done the Y direction yet. We will actually be doing that later this week, I believe, or next week. I think it's next week, actually. So that's just to make sure we understand what's going on here. All right. We're not quite done yet. That was part B. We had part C up here. Oh, sorry. What am I doing? Part A up here. Now we'll get on to part C, which was kind of the harder part here. So part C says the distance travels during the first and fifth seconds. So to me is it's saying how far does the car travel from this being time equals 0. So time equals 0. How far is it traveling in that to time equals 1 second? Okay. And then separately, it's asking for time 4 seconds to time 5 seconds, okay? So it would be the first second and the fifth second, okay? The first part is going to be pretty easy because we already know the initial velocity. The fifth second is going to be a little bit more difficult because we don't know the initial velocity here. Okay, we don't know this initial velocity, but we do know this initial velocity we said was 12.5 meters per second. Okay, so we'll get there. So the first one is pretty easy. It's just a distance based upon that first second of time. So we're going to use that second kinematic equation there because we're looking for distance. And we know the initial position, and we know the initial velocity, we know the times, and we know the acceleration. So just to be clear here, we have, this is for the time 0 to 1 second. We know x is going to be our question mark. We know the initial position is 0 meters. We know the initial velocity is 12.5 meters per second. We know acceleration is negative 0.5 meters per second squared. And we know the time here is 0 to 1 second, which is just 1 second. My T's are looking funny, sorry. All right, so I'm just going to plug that in here. So x is equal to 0 meters plus 12.5 meters per second times 1 second plus 1/2 times negative 0.5 meters per second squared times 1 second squared. All right, so we just plug in our calculator. Easy enough. So 1 squared is just 1 times negative 0.5 is negative 0.5 times 1/2 is negative 0.25. And then we're going to add a 12.5. And we get 12.25 meters in that first second. So that's how far it's traveling in the first second. Okay, now the fifth second is a little bit harder. We need to know how fast is it traveling. How fast is it traveling at the fourth, when it hits that 4 second mark, right? That initial, if you will, velocity at that 4th second. So if you think about how we can do this, we can actually figure out how fast it's going at that point by wondering about what is the final velocity from the very beginning, right? So how fast is it moving Vx after 4 seconds. Okay, so that would actually be the initial velocity at that time. Because the acceleration doesn't change, we know the time and we know everything else. We actually have to have the initial. Oh wait, it's asking you how far the distance it travels. So, sorry to make things a little bit more confusing. Distance traveled is another name for like the displacement, right? Which is just x minus x naught. It's asking how far it's traveling. We kept saying x naught is 0 meters. Well, at this point, over here, we don't know x is 0 as well, right? We don't know how far it's traveled at that point, but it doesn't matter because it's not asking us the position of the car after 5 seconds. It's asking how far it traveled, which is x minus x0. It's like the displacement or distance in this case. This is a little confusing, I know, but hopefully you get it. If you do have questions, please let me know. So let's just draw this out to make it clear. So at some point, this initial position of the car at t equals 4 seconds, we also need to know the initial velocity at 4 seconds so that we can actually figure out this distance here between the 4th and 5th seconds of motion. So we need to know we don't need to know x0 because like we just said, we only really want to know x minus x naught, and we need to know Vx0 at that 4 seconds. So what we're going to do is we're going to find Vx after 4 seconds of motion. So there's kind of two reference frames here. So the first one here, Vx, this is going to be after 4 seconds of travel. How fast is the car moving? So we know that its initial velocity was 12.5 meters per second. Man, I keep saying that. Let me just check. Yes, 12.5. All right. It has negative 0.5 meters per second squared acceleration. And we're saying how fast is it going after the first 4 seconds of motion. So we can just plug that in to our calculator. 4 times negative 0.5 is negative 2 plus 12.5 is 10.5 meters per second. So we know after 4 seconds of motion, the car is traveling at 10.5 meters per second. That is going to be our initial Vx0 at 4 seconds. Okay. So that's all we need to know to plug it into that second equation. So x is equal to x naught plus Vx naught t plus 1/2 axt squared. So I'm just going to subtract the x naught from both sides so that those reduce out, and I'm left with x minus x naught, which is ultimately what we're looking for, is equal to Vx naught times t plus 1/2 axt squared. Okay, I'm just going to plug in my numbers. I know my Vx naught now is 10.5 meters per second because that's how fast it's moving at the 4 second mark, times it's only going to travel 1 second from 4 seconds to 5 seconds. And then we have still going at negative, still decelerating or slowing down at 0.5 meters per second squared. And it's just 1 second again squared. So I'm just going to plug that in and I'll get the final answer. So 1 squared is 1 times negative 0.5 is negative 0.5 times 1/2 is negative 0.25 plus 10.5 times 1, which is just 10.5, and I get a final answer of 10.25 meters. So that's how far it travels in that 5th second, or from 4 seconds to 5 seconds. That problem was a little bit more complicated, that part C there. So hopefully you understood most of it. If you have some questions, please email me and I'll help you with that one. All right, and we're going to try what? That was just problem 25. All right, so let's move on to 27. Determine the stopping distances for an automobile with an initial speed of 90 kilometers per hour and human reaction time of 1 second for an acceleration of a equals -4 and part B for -8 meters per second squared. All right, so human reaction time. So what it means is that person sees something that they need to stop for. It's going to take them 1 second, which is actually pretty slow, to go from I need to stop to actually putting their foot on the decelerator or the brake pedal. And so for 1 second, the person in the automobile is going to be traveling at 90 kilometers per hour. And that's going to be included in ultimately our stopping distance. The other part of that stopping distance is going to be the deceleration or an acceleration of -4. So that person's going to slow down now at -4 meters per second squared and see how far it takes them to stop to 0. So let us write this down. So it's going to kind of be a couple parts here. So this part isn't going to change between the two. The car is moving at 90 kilometers per hour. They see something that they need to stop. So they have this initial position here. They're going to move to position X. This is going to take 1 second of time with them traveling at 90 kilometers per hour. At that point, they're going to hit the brakes and they're going to slow down now until a new position, X. Okay, and they're finally going to get to a stop here. So at the beginning of this, they're going to still be moving at 90 kilometers per hour. And then at the end, they're going to be moving at 0 kilometers per hour, or 0 meters per second. Okay, so we're looking for this whole stopping time from here all the way to here. Okay, let's maybe call this position 1, position 2. So really we're looking from x0 to x2, but we know that x0 to x1 is going to be the same because that second is always going to happen no matter what. And then how well the brakes work is going to determine that x1 to x2 distance for A and B. So let's start with just that initial, the distance that it's traveling during that reaction time. So so we have initial position we'll call 0 meters. We know the initial velocity is 90 kilometers per hour. The final velocity during that point is still 90 kilometers per hour because the person has not put their foot on the brake yet during that time. The time is 1 second. The acceleration in this part is 0 during that initial time. Okay, and we're worried about how far does it travel to position x1. All right, so let's just use that second equation. We have x is equal to x0 plus vx0 times t plus 1/2 axt squared. And we're just going to plug in our numbers. So this is going to be x1. It's going to start at 0 meters. It's going to be initially moving at, we actually have to do this first. So 90 kilometers per hour. We have 1,000 meters in 1 kilometer and 3,600 seconds in 1 hour. So that 90 times 1,000 divided by 3,600, and we get 25 meters per second. So Vx0 is going to be 25 meters per second. So let's plug that in, 25 meters per second times 1 second. 1/2 times 0 meters per second squared times 1 second squared. Oops, that squared should be on the outside of the parentheses there. Well, what's nice is this whole thing goes to 0 because anything times 0 is 0. So the distance it travels during that reaction time is 25 times 1, which is just 25 meters. So that's quite a bit, right? A second is really bad reaction time in this case, but some of the classes took reaction times actually, you got like 0.3, right? So much shorter, but you can imagine 25 meters is kind of a lot. It's almost 100 feet. All right, so I guess it's between 75 and 80 feet. That's going to be the same for both A and B, that initial stopping distance, because that's just pure reaction time. Now from x1 to x2 for part A and B is going to be different because the decelerations or the accelerations are different for both of those parts. So part A, we'll worry about how far it's traveling from x0 to x1. Well, let's do from x2 to x1. So now for this part, our x1 is going to be our initial position, and that is going to be 20. Well, do you want to do it this way? Yeah, let's do it this way. So 25 meters, right? That's our initial position. So x2 in this case is going to be our answer here. How far does it travel? Because we are calling x0 our 25 meter point, okay? You could do it saying it's 0, but then you have to add in the 25 later. So this way it just kind of adds it in for us. We know the initial speed during this time is 25 meters per second. We know the acceleration is -4 meters per second squared for part A. We don't know the time. So we don't know time for this part. Because at this point, foot's on the brake, we're worried about how far it's going to travel. The final speed, though, we know is going to be 0 because we want it to stop. Okay, so if I look at the variables given here, I'm going to move this over. All right, so I don't have time, so that means I'm going to look at my equation sheet, and I'm going to say, well, the only one is that third one. That's the one I'm going to use. All right. So we have Vx squared is equal to Vx0 squared plus 2ax times x minus x naught. I'm looking for x2, which is x in this case. Okay, so I'm just gonna, first I'm gonna solve for x by itself. So let's see. Subtract Vx0 squared from both sides, that those reduce out. Gotta do it from both sides of the equation. I now have Vx squared minus Vx0 squared is equal to 2ax times x minus x0. I'm going to divide 2ax from both sides, that those reduce out over there. And now I have Vx squared minus Vx0 squared over 2ax is equal to x minus x naught. So for x0, so hopefully you can see I'm just going to add that x0 to both sides, that those cancel out. And add it to this side of the equation. And I'm left with, I'm going to flip-flop the sides again, so I have x is equal to Vx squared minus Vx0 squared over 2ax. Plus x naught. Okay, I'm going to plug in my numbers from part A here. So Vx squared is just 0 meters per second squared minus 25 meters per second squared times 2 times -4 meters per second squared plus 25 meters. I'm going to plug that in and I get an answer of, so this is my final position, the distance I travel. Let me plug it in. So 25 squared is 625, and that's negative up top because it's 0 minus. The bottom is -8, so 625 divided by 8 is 78.125. And the negatives cancel out, so I'm left with 78.125 meters. Okay, so that's how far, x2 if you will, right, how far it's traveling during that stopping time. Part B is actually easier now because I already have the equation. I'm just going to plug in a different acceleration for it. So my initial position is still 25 meters. My final position is still my question mark. My initial velocity is still 25. Did I do that right? You have 25 meters per second. But now my acceleration is -8 meters per second squared. So you can see how much faster we'll stop. And then we don't have time. So we're just going to plug that into our equation again. And we already had the equation written down. So let me look at it. It's x is equal to bx squared minus vx0 squared over 2ax plus x naught. So I'm just going to plug in my new numbers in there. So I have vx squared is still 0 meters per second squared minus 25 meters per second. That all squared over 2 times -8 meters per second squared now plus 25 meters. Okay, and I plug in my equation and I see, let's see, 25 squared is still 625 divided by 16 now, and I get 39.06 meters. Okay, so with twice the deceleration, I get half the distance. All right, makes sense. All right. The next problem we're going to do is problem number 29. All right. A speeding motorist traveling at 120 kilometers per hour passes a stationary police officer. The officer immediately begins pursuit at a constant acceleration of 10 kilometers per hour per second. Now they're just playing with us, with the mixed units. How much time will it take for the police officer to reach the speeder, assuming that the speeder maintains a constant speed? How fast will the police officer be traveling at this time? All right, so we're worried about how much time will it take the police officer to reach the speeder, assuming the speeder maintains a constant speed? All right, this one's going to be quite a bit harder. You know what? I'm going to pause this video. I'll create another video for number 29 because this one's going to take a while and I don't want to make this video too long. So I'll pause this one and I'll create another video